These video notes are for chapter 15, sound. It'll be the first PowerPoint. So in chapter 15, we're talking about sound. We've just finished with waves. There are a lot of things that will be similar between this chapter and last. We'll start out by talking about sound, and you need to be able to draw a sound wave. You're going to kind of draw a pretend image that if you could see the actual air molecules. It is a longitudinal wave, kind of like the slinky. When we did push the slinky and the energy went in the same direction as the movement of the wave, parallel, that would be like sound waves. Now, sound waves, of course, travel longitudinally out in every direction, so they get bigger and bigger, kind of like a bubble being blown up or a balloon being blown up. The diagram we have here on the page shows you a sound wave moving from a speaker, which is the source, to your ear, which is the collecting and perceiving device. Notice that they're what looks like a transverse wave underneath. What they're doing is they're plotting the number of air molecules. Notice that where there are lots of air molecules, we call that a compression. Where there are not very many, it's a rarefaction. You need to know those terms and be able to label them on a diagram. Think of rare being where there's not so many, because that's kind of what the word rare means. So when we graph them, the low point is a lot like a trough on a transverse wave, and the crest is, or the compression is a lot like a crest. So we're making that analogy here. And should be able to label a wavelength. Of course, a wavelength would be from one spot on a wave to an identical spot on the next wave. Compression to compression would be a good way to do that. So we move on, and we see on the next page that we've got a familiar formula here, V equals F lambda. This is the same formula we used back in chapter 14, which was on waves. Now, I had folks come in to tutorials and say, I just can't solve these problems. I don't know where to start. Well, that's easy once you get practice. And actually, several people came in, and by the time they left, they were solving every problem using the same method. How do we do this in physics? Well, I'm giving you the formulas on these tests, so you have a place to look for the formulas. When you have a problem, circle the parts that it's giving you, and in this case we've got velocity, frequency, and wavelength, and you are going to circle the items that you have in the problem. So for instance, let's say that the problem said what is the velocity of a wave that has a frequency of 43 hertz and a wavelength of 1.1 meters. Well, you go in and circle velocity, frequency, and wavelength. You circle those three and then go look on the sheet, and it's kind of like shopping. You say, oh, well, here's one that has velocity, frequency, and wavelength. Plug in the things you have, do the algebra, and it's really all of physics is going to be simplified down to the level of kind of walk in the first day Algebra 1 stuff. So I'm going to give you this equation. I'm not going to give you the V equals velocity, F equals frequency, and lambda equals wavelength. You need to know that. But look over those, and if you need more help on solving the formulas, come in at Mega Lunch or come in during the tutorial sessions in the morning. So we move on. We're going to talk about the speed of sound. Sound travels in air at 331 meters per second at 0 degrees. If it's hotter, it travels faster. It's like when you're in the cold. You're in the cold, you want to huddle up and not go a lot of places. But when it warms up, springtime, you want to get out and run around. So it's the same with air molecules. They speed up when they're hotter. Sound travels faster in solids than in liquids, and faster in liquids than in air. Easy way to think of this is, let's say that I had the whole class lined up in the hall, and one person is going to tap the next guy's shoulder, and then when they get tapped, they're going to tap the next guy, and so on. If you're close together, that signal of tapping is going to go down the end real quick. If I have the person on the end raise their hand, that may take 10 seconds, maybe 5 seconds. But if you had space. Let's say that each person had 10 meters. Well, you tap one person, they've got to run 10 meters. Tap the next person, they've got to run 10 meters. That signal is going to take a lot longer to get down to the end. It's the same with gases. Solids are close together. They send a signal real quickly. Gases are spread out. The gas has to travel, then it hits, and then it sends the next the gas molecule forward. So you can see how gases and liquids are going to be a little slower. You know, the old train robbers used to put their ear down to the track, and they could hear the train coming maybe 5 or 10 minutes before they could hear it, like in the air. And I'm not saying go put your head on a train track, but you know, if you listened on a train track, chances are 10 minutes, maybe 5 minutes before a train got there, you would hear it on the track, because the sound not only travels faster, but it travels farther. So don't go around train tracks when there's trains there. Absolutely don't do that. But that was how they used to do it. And of course, those guys, they robbed trains. What did they know? So, higher the temperature, the faster the sound. Solids go faster than liquids, go faster than gases. Speed of sound at certain temperatures, there's an equation for that, and it's right here. Again, velocity T, V sub T is the velocity at a certain temperature. At 0 degrees, sound travels 331 meters per second. For every degree above 0, we add another 0.607 meters per second. So if this were 1 degree, we would put 1 times 0.607 and then add it to 331. If it were 2 degrees, we'd multiply 2. If it were 10 degrees, 10 times 0.607, and then we would end up adding 6.07 to 331. Really not that hard of a formula. You'll be given this formula on the quiz and the test, and you'll have a problem where you'll have to solve on the quiz and the test with that. So we move on and talk about detection of sound. This is going to reach across 2 or 3 different areas in the book. As far as the detection of sound, of course, we use our ears as our primary detectors of sound. And I want you to look at that ear diagram to have a basic understanding. The eardrum, which is called the tympanic membrane, is inside of the funnel of our ear, and that kind of separates the outer ear from the middle ear. The vibrations hit the membrane, and they go through 3 bones, and the 3 bones, the hammer, the anvil, and the stirrup are the common names for those. They're kind of set up to be a shock absorber, because if the sound hit that membrane and went directly with a straight bone into the next membrane, if you had a real loud sound or you had damage to this eardrum, it would rip right through the other membrane on the inside, and that would be some real serious problems. So it's kind of a shock absorber, those 3 bones. They vibrate the membrane on the cochlea. The cochlea looks like a big shell, like a cockle shell. It's a kind of a spiral shell, goes from big channel to smaller and smaller and smaller all the way to the middle. Inside there's a basilar membrane that has these little hairs standing up that are connected to nerves. The big hairs only vibrate with big waves, which are a low frequency. Remember, wavelength and frequency, those are opposites on a seesaw. The medium waves vibrate with medium wavelength. The small hairs in the very end only vibrate with high frequency, small wavelengths. So that's how the nerves send a message to the auditory nerve, to the brain. And in the auditory center, when you're 2 months old, 3 months old, we don't make a lot of sense of this. But as you learn, you also learn the different frequencies and what they mean and what the words mean and everything. And you get to translate what all those sounds mean. So here's a picture of the ear, and you can see where I have the hammer, anvil, and stirrup labeled here. You don't have those on yours. I think they call it the malleus, incus, and stapes. Those are the kind of the scientific terms for the 3 bones, but common names: hammer, anvil, and stirrup. There are 3 bones. That's a question on the review. Perceiving sound. Marin, Racine, and Galileo were the first ones who actually did experiments where they knew that frequency the highness or lowness of frequency was what caused pitch. And pitch is just that, the highness or lowness of frequency. Loudness of sound is determined by the amplitude of the sound wave. Like that diagram we had on the first page, the more air molecules, the higher the graph of how many air molecules, and the lower the the rarefaction, that gives you a high amplitude. So there's more energy with high amplitude in sound. Sound intensities are determined and measured by a power of 10 base scale called the decibel or sound level scale. And the bell is where we get decibel. Bell's a big unit, so we use a decibel, tenth of a bell. And that bell is named after Alexander Graham Bell. That's where the unit came from in his honor. A 10 decibel increase in sound is actually a doubling in the loudness. So that shows you how two ways to talk about loudness compare to each other. A tenfold decibel is doubling of loudness. Humans generally, when they're born, can perceive from 20 to 20,000 hertz. When you get to be teenage years, probably have lost even a little bit of that, especially if you listen to loud music with headphones on. Might get to maybe 20,000 to 16 or 17,000. And, average human is somewhere less than 20 to 20,000, but that's what we call the perceivable range. Doppler effect. Probably everybody has heard a train or a car go by you honking a horn, and you hear it go wah, like that. That sound goes from a high pitch to a lower pitch. Yes, it gets louder when it's closer, but this doesn't really have anything to do with the loudness. It has to do with the pitch or frequency. And this diagram is a good picture of what happens in front of the car. The waves are being scrunched up so they're closer together or higher frequency, and you hear a high pitch. When the car passes, it's stretching out the waves, and they have a perceived lower frequency. So it's going to be a lower pitch. And that's what we call the Doppler effect. There's a formula that can be used in several ways, and I'm going to give you kind of the basic formula here. So I'll have these two formulas, although I'm not going to have the receding and approaching. You need to spend a little bit of time looking over those so that you know. But the F of the source, that would be the actual frequency of the horn. The V, without anything on it, that's the velocity of sound. So for the top and the bottom, the velocity of sound will be the same at that same day. The V of source would be how fast the source is moving, receding, which means away, or approaching, which means towards you. So you will have a question like that on your practice pages. You also have one on your test. So, it kind of separates the hundreds from the 95s. A little tougher formula, but not incredibly tough. So look over those, and like I said, you'll have a practice page where you'll get to practice some of those and get to see the answers right there. So that finishes up notes for day one on sound. Work on your review. The videos and the PowerPoints and all that will be out on a website at www.landerson.net. If you go to that site, the main page has a little box with some little sub boxes in it. Middle bottom is physics. So click on that and then go to chapter home pages. You should be able to go to 15, which is chapter 15. The review, the PowerPoint, all those will be out there. They'll be connected. There's also a link to the other physics book that we had a couple of years ago. If you don't have a way to log on to the book, make sure you see me. I want you to be able to log on to the textbook, because my reviews, most of them can be answered pretty much by the book or by the PowerPoint, or some combination of that. But do make sure that you go on, look at the website, see what the resources out there that can help you, and work on your review. If you have questions, like I said, come into tutorials.